I know it's not up there yet, but we will finish with just like 3 slides from the hydrogen atom and then go to reviewing starting at the beginning of the semester. So tell me what you learned about bonding and anti-bonding from last class period. Right, I asked you that at the beginning of last class period what you know. Is now what you know differently.
So I understand the reason for the spatial anti-symmetry in the hydrogen, in like a hydrogen molecule, or any type of, I don't know what kind of systems else it would work for, because you're just talking about systems with 2 electrons, right?
We were specifically looking at 2 particle systems.
Okay, so yeah, so because the triplet state has a symmetric spin, it has to have anti-symmetric spatial wave function. That's higher energy.
Yeah, it was just saying.
And they repel, as we saw from that separation calculation.
Yeah. It was nice to have the overlap from the last part of the spin-spin coupling perturbation theory was kind of similar to that, so that's interesting.
Okay, so we have some understanding here, and so these are just reviews of what you said. When you have 2 spark particles, you can have either the triplet state, which is a symmetric, or the singlet state, which is an anti-symmetric. And it was using the ladder operators that we were able to determine which one was which. That is, which one the S equals 1 went with, and which one S equals 0 went with. And then with fermions, you have to have an overall anti-symmetric wave function. And so that's what you were saying, overall anti-symmetric, if you have a symmetric spin state, and you have to have an anti-symmetric spatial state, and vice versa. And so that's where we get the bonding and anti-bonding orbitals from, because if you have the anti-symmetric spatial state, then they repel. I think I got that one right. Actually, I got to look back at it. I don't remember which one repelled suddenly.
You said anti-symmetric spatial state.
Yeah, I know. I'm just not sure if I said it right. Which is a little disconcerting, right? So it should say the singlet states are anti-symmetric, so we combine 2. In addition to the singlet state, the spatial function must be symmetric, which is bonding. So there's making sure that it's correct. So that's our review of the hydrogen atom from everything that we've done starting last class period. Okay. So any questions about the hydrogen atom to finish that topic up?
Would you ask us questions about the neutron star and the white dwarf things?
The only things that I would potentially ask you about were how the particles being fermions affects that. Right, because if they were bosons, you wouldn't have that problem. They would just collapse.
Yeah, there's no degeneracy with bosons.
Right, they can all be in the same state.
Okay.
So with this final exam, what's the spread or distribution going to be like? Is it going to sway towards the hydrogen atom?
Yeah, it will be weighted toward the hydrogen atom. I mean, everything is built toward that. It's our ultimate goal. So we had things we had to understand along the way. But yeah, it's definitely biased toward the hydrogen atom. Okay, another question, something we didn't talk about. If you read the textbook, we actually skipped over, I think, the section on helium. And you had things like orthohelium and perihelium. Did you take a chance to look at that at all? I mean, you didn't have to. Okay, that's something that, as chemists, it would be good to understand, to look at, orthohelium and perihelium. I mean, whoever talked about that? Have you ever heard those terms in chemistry?
I don't think we have.
And so that's something, I mean, I'm not prepared to lecture on it, I didn't prepare, but that's another thing that would be useful to look at. And what we've learned about the hydrogen atom is broadly applicable. So we can take what we've learned about the hydrogen atom, we can apply it to things like a carbon atom or a uranium atom. The underlying fundamental of what's going on with all of chemistry is built on these wave functions and the shapes of the orbitals. And of course, when you have a molecule, the molecular orbitals are a much more complicated quantum physics problem. You know, calculate the probability density for a molecular orbital is, well, not something I can do. You know, because it's more complicated than just, oh, well, we take the two orbitals and we overlap them, because they're affecting, you know, this nucleus is affecting both of them, this nucleus is affecting both of them. Each electron is affecting the other electron. So the problems get much harder. And I know at the end of a class like this, that's one of your difficult classes, honestly. And then to hear it gets much harder is not very exciting. But maybe, you know, helps you feel a little better that, yeah, I've only taken 2 classes that are above this class in level in quantum mechanics. And so my knowledge isn't really that much more sophisticated than what we've had in this, you know, as somebody who's a physicist. So it's a specialized group of people who really understand.
So would this pop back up in grad school?
Okay, so let's say you go to grad school in chemistry. I can only refer specifically to the way things were at Washington State University in the late 80s, early 90s. In the late 80s, early 90s, they assumed that the class physicists took, basically this class, was not sufficient, and so they had to essentially retake this class. And they also required all chemistry majors to essentially retake this class. And the chemistry majors, at least we were told, they considered it their readout class, the hardest class in all of graduate school for them. So does it occur? It should. It did there. It was just one class, and it was, well, as you can understand, it's a hard class.
How much harder was it than this class?
I didn't really think it was harder. I mean, that's my recollection from a long time ago.
I mean, was it covering the same topics in kind of similar order?
Yeah. It was double listed as Physics 450/550, and it was intended for both first-year graduate students and senior physics majors, this is intended for senior physics majors. Okay, so starting at the beginning, origins of quantum mechanics. You should still have that knowledge of where it all began and what the purpose was of quantum mechanics. You know, was it, you know, when we look at Schrodinger, was he looking for quantized energies? No. He was simply starting with a wave. If a particle can be a wave, then Peter Debye said, well, they should be able to have a wave equation. And so he found a wave equation, the Schrodinger equation, which we now know is not the only possible wave equation. It's the one that gives you the solutions for energy. So you can have other wave equations, like one of the solutions for angular momentum. So we did a homework problem. Well, actually, now that I think about it, it was technically kinetic energy, the treating Cn as a dumbbell. So technically that was using the Schrodinger equation and doing it for energy. But in practice, it was doing it for angular momentum squared. So we could have just said, find the solutions to the angular momentum squared operator for this, and then find the kinetic energies, and you would have been able to do the problem just a different set of instructions with the same outcomes. So there's different equations you could use for your wave equation, but the first one was the energy one, and it's still considered, you know, the most universal one that we use. So we have the matrix method. Well, that was kind of a quantum approach right from the outset, because Heisenberg was saying, okay, so we've got these values that are observable. We have this value, this value, this value. How can I make sense of it? And we've learned to use the matrix method now in a manner to solve problems. So you can have a Hamiltonian that says, okay, we have these two energy states. And so you can make your operator that is a matrix with those two energy states on the diagonals. And then you can find the eigenstates that go with those. And you can move on in that direction as well. It's fundamentally the same, even though mathematically it feels entirely different. So operators, we had two ways of looking at operators. One were operators, they're functions that act on functions. And using that whole eigenvector, eigenvalue relationship, if a function is a function of the operator, so function and function of the operator are two different meanings. If it's a function of the operator, then the operator acting on the function will give you a value times the original function. And that's what defines our eigenstate. And so we had mathematical functions for the analytic or the calculus way, or we had matrices. So our operators were square matrices, and when you find all the eigenvalues, you might have a square matrix that's not diagonalized. You can still find the eigenvalues, and then once you find the eigenvalues, you can make a matrix that is diagonalized from those eigenvalues, and that will be another version, just a rotated coordinate system, if you will, of the same operator. And of course, that makes it easy to find the eigenstates, because then the eigenstates would be 1, 0, 0, 0, or 0, 1, 0, 0, 0, and so on. So when it's diagonalized, your eigenvalues are just the trace elements, and then you have easy eigenstates, unless degeneracy occurs. If you have two different states that give you the same energy, we call that degeneracy. And in that case, it kind of screws things up. We didn't talk about that aspect, so it's not something you have experience with. So you should be able to work with the matrix method to find the eigenvalues of the matrix, to find then the eigenstates of the matrix, to find the rotation matrices or symmetry, similarity matrices to rotate the coordinates so that you have the diagonalized system.
How do you find the eigenstates from a diagonalized operator?
Well, from a diagonalized one, it's the same method, but it turns out to be very simple. So if it's a diagonalized operator, like let's take a 3-state operator, and let's say our operator is 1, 0, 0, 0, 2, 0, 0, 0, 3. When you have your operators like this, you can instantly read, and you know that eigenvalue 1 is equal to 1, eigenvalue 2 is equal to 2, and eigenvalue 3 is equal to 3. Right? If it's diagonalized, the diagonal elements are the eigenvalues. And so then I take that operating on ABC is equal to my eigenvalue times the same ABC. And so I'm going to have the equation A equals lambda A 2B equals lambda B, and 3C equals lambda C. Right? Those are the three equations I get. Now, I've done this very generically. But I have three values of lambda. If lambda is 1, the only way this can be true is if B equals C equals 0. Right? Because you can't have, or if lambda is 1, yeah, then you can't have 2 equals 1, can't have 3 equals 1. And similarly, if lambda equals 2, then you have to have A equals C equals 0. And if lambda equals 3, you have to have A equals B equals 0. And so then I think we can all normalize these these vectors that have only one component that's not 0. And so these will give us 1, 0, 0, 0, 1, 0, and 0, 0, 1. I mean, you could have said 0, 0, C and then go through the normalization process, and you have C squared equals 1. And, well, C mod squared equals 1. With the plethora of angular differences you could have. So you could have, as I said in class earlier today for the college physics, e to the IA instead of 1. But why would you do that? So is that...
Yeah, that makes sense.
So that's... The diagonal form is the one that then gives you the easy eigenvectors.
Okay. And like we had on that last homework with making the similarity matrix,
Mm-hmm.
is that kind of similar to?
That's the point of it. The similarity matrix will diagonalize it, so you have this simple case.
Yeah. Is that kind of the level of difficulty that you would have on the test?
Yes. Okay, then the statistics. By this point, we've actually moved a lot away from statistics because we, I assume, understand them. But we started out, we didn't understand them, so we had to learn about how we get probability. What is the method for finding probability once I have my wave function?
Square.
Wave function mod squared. And remember, of course, the complex conjugate times the original is important. And that's always going to give you a real positive value. Okay, so if we want to normalize, it plays into this because we have the probability. If we are doing everything in position space, you know what? We did everything in position space. I don't think I did anything in momentum space, did I? Yeah, I don't think so.
Very little.
Yeah, we did.
Did we do them?
We did, it was later on, but we did find the solutions to the momentum state, and we saw that it wasn't like, there were actual eigenstates, it was like continuous.
Right, I remember what you said, about the free particle.
Yes.
Yes, and so we shifted from position space to momentum space, yeah. So basically we'll stick with position space, right? Don't, just one more confusing factor to use that essentially Fourier transforms to go from position space to momentum space, or vice versa. So if I'm in position space and I want to find normalization means the sum of the probabilities of where's the particle in all location of if the particle is at this location for all locations. And by definition, that has to be 1. So the normalization idea is a pretty simple idea. And of course, you're going to have to be able to do that kind of calculation. Mean expectation value. The expectation value is just the mean. And so we take the probability of a value times the value, and we integrate that over all space. And since psi star psi gives us the probability, and operator psi gives us the value, that's why we have to have psi star operator psi. And then the standard deviation, of course, you've done that a lot. The standard deviation we had to find, for instance, expectation value of x and expectation value of x squared. And the standard deviation was the difference, the square root of the difference between the expectation value of the square and the square of the expectation value.
And those kind of equations would be given.
Yes, yes. So it's statistics because quantum mechanics is probabilistic. It's not deterministic. It doesn't tell us what's going to happen. It tells us what the probabilities are of outcomes. And so that's why it's so heavily statistical. So here I have a short history of the wave method and how you do it. So you separate your equations into the time independent and the time dependent part. Do you remember the condition that was necessary for that to be a correct or possible mathematical operation?
Potential energy is a function of position only.
Right. The potential energy can't be time dependent. It has to be position only. Technically, if the potential energy was time dependent only and not position dependent, you could do it as well. But in almost all of our problems, and certainly all the problems we did, the potential energy was position dependent, and so it works. And so then we have the time independent and the position independent. The time or the position independent solution always gives us the same result. You had one test question where you had to say, okay, so assuming that you correctly found your position wave function, what's your overall wave function? And you had to realize, okay, so I take the time-dependent wave function, which is always e to the minus iet over h bar, and just multiply my spatial by that. And since it has e in there and e becomes quantized from your spatial part, you have a different time part technically for each state because you have different energies for each state. So you solve the stationary states. The stationary states are not states where time doesn't exist. They're states that are constant in time. And then you combine the two, as I just said. The wave functions must be normalized and mutually orthogonal. What does orthogonal mean in a practical sense?
Well, I know the expression, but mutually perpendicular across all space.
Yeah, mutually perpendicular to each other. So all of them are mutually perpendicular, which in our brains only works in 3 dimensions or less. But in math can work in infinite dimensions. And how do we do, right, for math, we determine if they're perpendicular, if a dot product, if A dot B equals 0, then A is perpendicular to B. Like that's what we learned in math. How do we do it in our space for quantum? We do the inner product. We do integral of psi A star psi B dx over all space. So this is equivalent. The inner product is the same as the dot product. And so our orthogonality means the inner product between psi A star and psi B has to be 0 unless A is equal to B. And if A is equal to B, then the normalization means that they have to be 1. And so we put here, we do the delta AB because that covers both normalization and orthogonality. Now, the matrix method, the Heisenberg way, he set aside his concerns with I can't determine what the location is and just focused on what's observable. In quantum mechanics, we made a big deal about observables. Observables, first of all, these are things you have to be able to measure. And if you can measure them, they're all real. We haven't figured out any kind of way to observe something that's imaginary in value. And so all of your observables have to be real. That's actually the reason that our operators have to be Hermitian, because Hermitian operators give you real eigenvalues. And so there's the second line. Operators are Hermitian because they give you real eigenvalues. Those eigenvalues are observables. So give me examples of observables, just to make sure we know what we're talking about. Position, momentum. The other obvious one is energy. Probably too obvious for you to be thinking about it. So those are the kinds of things we've been dealing with for our operators, and the observables associated with them are these real things. The wave functions in the Heisenberg or the matrix are one-dimensional. So they have for a ket, and so I suddenly jumped into the broad ket notation because it's just the easiest way to name it. I could have said psi versus psi star. For the ket, you have a column matrix. For bra, you have a row matrix. And since the bra is complex conjugate of the ket, when you convert from the row matrix to the column matrix, you take the transpose and you do the complex conjugate of it. Wave functions live in Hilbert space. That's the space. A Hilbert space is a complete space with inner products. So you can calculate that for all of your vectors, and it's complete. What does it mean to be complete?
Spans all space.
Spans all space, which means that essentially you have a unit vector in every possible direction. That's what all of our psis, psi sub A, psi sub B, are, those unit vectors in each direction, so that any possible vector can be written as so much in the A direction plus so much in the B direction ad nauseum. Yeah. So, got that one covered. We're already up to chapter 3. We may not have to meet tomorrow. I mean, yeah, we still got 20 minutes, and I've only got to get through chapter 4. And actually, I've only got to get through chapter 3 because we started the hydrogen atom for chapter 4. So, chapter 3 was a math chapter. Neither of you had linear algebra, so it was all new. So this is where you learn those linear algebra techniques, things like how to find the eigenvalue of a matrix and how to find the eigenstates of a matrix. And of course, this Dirac notation, which I am guessing by now feels pretty natural to you, even though it was something you never heard of, I once again assume before, meaning of their product, uncertainty relations. That's one thing that I have. Wow, I'm finishing a day and a half early here. That's the one thing I haven't talked about that remains, uncertainty relations. How did we get the uncertainty relations?
I don't remember how we got there.
Yeah.
I know.
That'd be good to review.
Well, we talked about Heisenberg's uncertainty relation at the outset, like in chapter 2, I think, maybe it's chapter 1. And we said that he showed that for Gaussian distributions, that the smallest product, that you always get the smallest product of uncertainty, and it always had to be greater than or equal to h bar over 2. But then when we got to chapter 3, we revisited it. And I believe we took the expectation value of the derivative of time for our starting point. We had commutators that came in, and we ended up finding this uncertainty relation between two variables has to do with the commutator between the Hamiltonian and the operator. And so, of course, yeah, we're not going to revisit the whole derivation there. But it turns out you can calculate an uncertainty relation between any two operators. And if the two operators commute, what you get for your uncertainty relation? 0, assuming the operator is not time dependent. So if the operators commute and the operator is not time dependent, then you just have 0 for the commutator. What does that mean for the commutator, for the uncertainty relation? What does that mean if the uncertainty relation is 0?
You can know exactly where they are at the same time.
Well, exactly what the values for those operators are at the same time, yes. So you can know both at the same time exactly. And so in my mind, it has always been, if they commute, I can know them both at the same time exactly. And in fact, it's very simple. If I have A operator, B operator acting on psi, if they commute, then it means I have the same thing if I do AB or if I do BA. And so I can know them both at the same time because I get the same thing regardless of the order, which means I can move them past each other without changing anything. So if they commute, you can know them both at the same time. If they don't, you can only know one and not the other, which played into with our hydrogen atom. We saw that angular momentum squared commuted with one of the 3 components of angular momentum, but each component didn't commute with the other components. Well, if you want to be technical, angular momentum squared commuted with each of the components, but each component doesn't commute with the other. So you can know angular momentum squared in any one of the 3 components. And then we just made an arbitrary decision. We called it Z, the one we can know. So make sure you can do those commutators. You almost certainly have to do one.
Would you most likely put one that has angular momentum in it, or?
Because that's something that we focused on with the hydrogen atom, yes, I would most likely put one that has angular momentum in it. And 3-dimensional problems, yep. Chapter 4, getting back to the hydrogen atom. So this is, I don't know if we need to go over it again because we went over it yesterday. For the hydrogen atom, we started with 3-dimensional problems. And yeah, this is now repeating. I've covered everything I intend to cover for the semester, including reviewing for the exam. So what would you like to do for the balance of today, as well as 10 minutes today, 15 minutes today, and class period tomorrow?
Do you have any review problems that would be good to go over together?
I can make up a problem now and work on it, and then I can have some that actually would be worth thought out for next class period.
How about for today, then we just go through the questions, because I have a couple.
Okay, yeah, fire away.
Okay.
Put me on the spot.
Okay, so like with the eigenstate relations, you said we weren't going to have to actually rederive the spherical harmonics in the radial solution. Should we know what those equations are, like be able to give you those?
You mean, should you have
Like
the Legendre polynomial memorized?
Or just like the shorthand of it, like with the YLM equals.
You should be okay with YLN.
Like be able to write it down.
Just YLN, not the other part of the equal sign.
Okay.
Right, because it's just asking way too much to have you memorize those solutions. At least I think it is.
Will the test probably be like double the length in terms of like twice as many theory questions and twice as many calculations, or?
It probably won't be twice as much. It'll be more, but not twice as much. Because, I mean, it takes time to do the big problems. And the more big problems you have, the more likely you are to hit one that takes you longer than it should have. Just like you don't remember. I know I've had this where I know how to do everything, and I just don't remember one piece, and I sit there for a long time not remembering that one piece. And yeah, so it wouldn't just double because it doesn't work that way.
Tomorrow, could we focus on like a commutator problem and a wave function problem instead of like the matrix? Because I think we're both good on matrix.
Yeah.
Okay, so you said something with commutator and
Like the analytical.
Yeah. Like what kind of a wave function? Like would you have us give us a potential energy function, tell us to graph it, and then have us find the solutions in different regions? Like would you do that again, or?
I wouldn't give you the whole problem for time purposes. So and once again, of course, you're not in the college physics this year, but he is. I would give you potentially pieces. So this is the result up to here. Now go from here to here. Just because of time. And as you've seen on tests, I may ask you to describe the steps that you would use and not do the work. And in that case, I could ask you to do the whole problem because you're just describing each step and not having, the work takes a lot longer than describing each step.
Yeah. As far as like the similarity to what the homework has been, would you ask us questions like, since it's going to be focusing heavily on the hydrogen atom, would you ask us questions like we've had on the past 2 homework assignments?
I think that there's always a fair amount of similarity between the homework questions and the tests. Would you agree or disagree with that statement? Because I think it's true, and I think it'd be similarly true for the final exam.
I would tend to disagree. Like, I don't think that it's that closely related.
So it's always good to get the student's perspective.
Yeah. Would you give us something that's kind of like applying the concepts from the NMR? Because we found the more frequency, right? Would you kind of ask us something that could be applied to more of a chemistry scenario or something?
Within limits. I'm not going to give you something that you haven't seen.
Okay.
And so I could ask you something like, what is the Larmor frequency? Or what are the gaps between the energy states? But I wouldn't say, so this is the actual spectrum, what is it, type of things.
Yeah, if we could just go over those 2 questions tomorrow.
Okay, so one was doing a commutator, and what was the other one?
Finding this, going through, we have the wave function method or the analytical method and then the matrix method. Doing not the matrix one, the analytical thing, wave function method, finding solutions and all that stuff for the problem.
With the problem.
I don't know.
We did it in 2 cases. We did it for the quantum harmonic oscillator and then for the hydrogen atom. And the reason we did the quantum harmonic oscillator was A, because that is realistic, and B, because you have fundamentally the same techniques when you're doing the hydrogen atom.
We should go through the one for the hydrogen.
I think that would be
okay.
Useful.
Yeah.
And then if we had extra time, just already think of chapter 4 is. What do you want to go over?
Spin stuff makes sense to me. I guess I kind of got confused a little bit during the discussion. I think it was on time. maybe doing another cross product example.
All right, well, shall we call it a day and
Yeah.
Sure.
reconvene tomorrow?